Okay, we're going to continue on lecturing chapter one of those four, I think it is. So last time we started talking about the atom. We talked about different types of properties of the atom, including atomic number, mass number, how to calculate the number of protons, electrons, neutrons. So remember that when we do look at the periodic table and we do look at, a symbol and the number that's above it, as we talked about, is the atomic number, which is the number of protons there are. We also talked about the mass number, which is the number of protons plus the number of neutrons. And remember that you basically can use both of those to determine how many neutrons there are by subtracting the mass number from the atomic number. When we do write a symbol, for example, it usually looks something like this. And up on top is the mass number. And on the bottom there, left is the atomic number, which is number of protons. Again, another common way sometimes it is written the symbol and a number afterwards, which represents the mass number in this particular case. We also talked about that it is really the atomic number that's the most important, which is really the number of protons. The number of protons really determines what element you're talking about. As we talked about last time, if you look at the periodic table, there is no atomic number that repeats, which means if you know the atomic number or you know the number of protons, you will know exactly what element you're dealing with. And if you don't change the protons, you'll never change sort of the element. And that's basically what happens in basic chemical reactions. All that really is involved are electrons, which means that we do have, like we talked about, that conservation of those elements. We really don't change elements in a chemical reaction. Things just rearrange. We also talked about that if we had something with charges, and if we do have something with charges, those are what are known as ions. And those are things that have charges. And there's two types, which are cations, which are positively charged, and there's anions, which are negatively charged. And really the way that we sort of achieve those is really changing the number of electrons. Again, we don't change the protons, otherwise we change the element. So if something had a positive charge, like say magnesium, with a +2 charge, it would have, in terms of number of protons in this case, 12. Because it has a +2 charge, the number tells you how many electrons it lost in this case. The positive tells you that it did lose electrons. So it would have only 10 electrons in this case, which are negatively charged. Again, that is where that +2 comes from. In this case, we would still take the mass number minus the atomic number to figure out the number of neutrons, just like we normally would do. And we get a cation by the loss of electrons. The anions are different. Basically, they're going to gain electrons. So if we look at, say, oxygen here with a -2 charge, and we'll do like 16, for example. This oxygen, again, in terms of protons, would be the atomic number, which would be 8. It has a -2 charge. So the minus actually means that it gained electrons. And the 2 is really how many it gained from a neutral oxygen. So in this particular case, it would have 10 electrons, giving us that -2 overall charge, which again is where that actually comes from. So when we do our things that do have charges, it is just the electrons that change. And again, either loss or gaining electrons will result in either a cation or an anion that has a positive charge or a negative charge. Any questions on that there? The last thing that we also talked about is really important to remember, and a couple of things that people do screw up on in terms of these things is, again, the mass number is not on the periodic table. So that number that's below the symbol is not the mass number. That is the atomic mass, as we'll talk about in a later chapter. But when you do calculate protons, electrons, neutrons, mass number, atomic number, they all need to be whole numbers, positive whole numbers. And as we talked about last time, pretty much none of those numbers on the bottom of the symbol there. So to remember it. Any questions on that stuff there? Okay. So isotopes, as we also talked about, isotopes are really the same element, but they do have different masses, and they have different masses because they do contain different numbers of neutrons. And that's also one of those things that is incorrect in Dalton's atomic theory. Remember, he said that all atoms of the same element are exactly the same and identical. Again, that was not so correct because of the existence of isotopes, which are the same element. Obviously, they are different because they do have different masses. Now, again, in normal conditions, isotopes do work sort of the same way as each other. And a lot of times isotopes of elements are radioactive. So in a lot of times people will use radioactive versions of isotopes of elements to do sort of research. For example, I used to do research on copper, and we would use radioactive copper 64. And we could follow pretty much where the copper went, like in the body, by following basically the radioactivity. The radioactive version of copper and regular copper will pretty much do the same sort of chemistry and stuff in the body and stuff like that. So it's a very common way in laboratories that people use sort of radioactive isotopes of elements, and you can really sort of follow along where perhaps that element goes in the body, what happens to it, by really following the radioactivity. So it's a very useful sort of aspect of isotopes. Any questions on that there? Okay, we're then going to talk about the periodic table. The periodic table obviously is our arrangement of elements. It gives a good amount of information. If I come back here, maybe not, come back. Gives a good amount of information about the different elements. A couple of things when we look at the periodic table is we do use the representative numbering. So if you look up on top, you'll sometimes see some different numbers, like we see 1A, then we see some numbers here. Sometimes these guys will also have like B's in front of them and so forth. We actually use the representative numbering, which is the A numbering. So when we look at a group on the periodic table, groups actually go down, and we do use this numbering. So this is group 1, this is group 2. We skip all the center. This is group 3, group 4, group 5, group 6, group 7, and group 8. So we usually use that A numbering, which is usually what is referred to as a representative numbering when we're talking about groups, which go down, up and down there on the periodic table. 1, 2, skip the middle, 3, 4, 5, 6, 7, and 8. So a group, or if you're old like me, maybe you call it a family still. Most people don't call it families anymore. Most people do call them groups. And again, as I just mentioned there, 1, 2, 3, 4, 5, 6, 7, 8, skipping the middle. One also important thing is in group 1 over here, hydrogen is not part of group 1, even though it is sitting on every periodic table right there above lithium. Group 1 actually starts with lithium. So group 1 actually starts with lithium. But again, you will see hydrogen there pretty much on every periodic table. And years ago, you used to see hydrogen like plopped over here on this side as well. There was sometimes be on both sides. A period goes from left to right. So this would be like period 1, period 2 going this way, period 3, period 4, period 5, period 6, and period 7. So those are periods that go left to right on the periodic table. Now, as we also talked about, the atomic number obviously is the number of protons. And that is obviously what we were just talking about that we can find on the periodic table. Now, when we look at the periodic table, it is really broken up into sort of 3 main categories. and those are metals, nonmetals, and metalloids. And metalloids are also sometimes called semi-metals. Now, pretty much on most periodic tables, you could kind of see this, what was sometimes referred to as like a staircase kind of coming down. And again, if you look on the one up there, you can see that kind of that dark line kind of coming down like a staircase by boron. So pretty much to the left of the periodic table there, that is where we find metals. To the right and upper part of the staircase there is where we find nonmetals. And obviously on the staircase there is where we find our semi-metals, our metalloids. Some books also include boron in that. I think your book might, some books don't, but that's sort of the staircase that comes down. Now, let's talk a little bit about metals. We talked about, I think, earlier as well. Metals is a good conductor of heat and electricity, is able to be hammered into sheets. You can pull it into wires. It typically has a shiny appearance. For the most part, most metals are going to be solid at room temperature. The one exception is mercury, which is why on most periodic tables, if you look at it, it's blue. And that is a liquid on, in most cases, mercury, the way it comes. By the way, this guy right here is which element? That is hydrogen, yeah? And hydrogen is a non-metal, yeah? And so that is also why hydrogen is not really part of group one, because those are metals, but it happens to just be placed over there. So hydrogen is a non-metal. And that's why, like I said years ago, on some periodic tables they used to even have in this school, you would find hydrogen over here because it's technically a non-metal as well. It'll be on both sides. But most of the time it is found over here. It is a non-metal. It is not part of group one again, because everybody else in group one, as you can see here, they're all metals. Also, if you look on the periodic table, there's those two rows on the bottom. I'll draw it on top, but the two rows on the bottom here, those are also metals as well. So those guys are also metals on the bottom two rows, where it says uranium and lanthanide and actinide, LAAC. Those guys are also part of metals. Now, nonmetals, on the other hand, have a more opposite sort of characteristics. Obviously, the metals, they're pretty much bad conductors of heat and electricity. They're also dull and brittle, but they also have a more variety in terms of states. So a lot of nonmetals are gases like nitrogen, oxygen, chlorine. Some are liquids and some are solids. So you get a much more variety in terms of the sort of states of those elements. Also, a lot of nonmetals, if you remember, are our diatomic molecules, which are our elements like H2, N2, O2, F2, Cl2, Br2, and I2, right? So those were our elements that are also diatomic molecules. So a lot of those guys come naturally like that. And that's pretty much like here and like down that row right there. Now, our semi-metals are our metalloids, again, for sort of overlay here, again, coming down here. These are really guys that have properties that basically fall on both sides of where they are on the periodic table. So metalloids will have, a particular metalloid will have properties that are some that are very similar to what we see in metals. And that same element will also have some properties that are very similar to what we see in non-metals. So it does sort of make sense if you think about sort of where they're at. You got all these metals, and then we're going into non-metals. So these guys sort of have properties that fall on both sides of them. They have, you know, some that are would be considered more metal properties and some that would be considered more non-metal properties. Now, some elements and groups have special names, and there's a few that you do need to know. So starting over here again in group one, these are the alkali metals. And again, that is with lithium being the first member of that, not hydrogen. Right next door in group number 2, those are the alkaline earth metals. And that is your beryllium, your magnesium, your calcium, and so forth coming down here. Group 7, which again, 1, 2, this being 3, 4, 5, 6, and 7. These guys here, which is our diatomic guys, fluorine, chlorine, bromine, those are the halogens. And we'll see it on the next slide. But right next door at group number 8, those are the noble gases. And you do need to know the location, obviously, of those groups and their special names. So group 1, alkali metals. Group 2, alkaline earth metals. Group 7, the halogens. And group 8, the noble gases. By the way, group 1 and 2 are alkali and alkaline earth metals. Group 1 and 2 is where a lot of strong bases come from, like acids and bases. And when you say the word alkaline, it means basic, really. It means it's another way of saying basic. So things like sodium hydroxide, which is strong base, potassium hydroxide, also a strong base. So a lot of them do come from group 1 and 2 on the periodic table, where we find those guys. So a couple of things about our halogens. They are very reactive nonmetals. They react with metals to form ionic compounds. And they also can be acids, like we've come across a couple of acids before that involve a halogen, like HCl, which is hydrochloric acid. Basically, if you put a hydrogen and H plus on any of those guys, you get hydrofluoric acid, you get hydrochloric acid, hydrobromic acid, hydroiodic acid. So a lot of them do make that. Fluorine is a kind of a pale yellow gas, chlorine a pale green gas, bromine kind of like a liquid with some vapor over it, and iodine is that purple. And remember, we did the iodine where we did the sublimation, right? We heated it and all the fumes that came up was very purple, right? So that was the iodine that we saw there in lab. The last group, as I mentioned before, are noble gases. Noble gases means that they are sort of set apart. Noble gases like helium, which it does start up here with helium, which is group 8. Helium, neon, argon, krypton, they're what are referred to as being chemically inert, which means they pretty much don't react with anything except themselves. They are also what are referred to sometimes as being monoatomic, which is a fancy way of saying they basically come as ones, like helium comes as basically one atom is the way it comes, different than something like nitrogen gas, which comes as 2 atoms together, diatomic as well. Now, there are 2 rows that are set on the bottom here. And if you do follow the numbering, if you look here, this is 56, that's 57, and then we jump to 72. The elements that are missing are actually right here, 58. This row technically goes right in there. And if you follow the numbering below that, it goes from 89 to 104. This is 90 right there, which technically goes after that element. Those guys technically go there. They are called the lanthanized and actinized because those are the 2 elements that they should follow in the periodic table. But if they did that, the periodic table would take up more of the wall, right? It'd be really spread out. They only had 1 room in this campus in the old building where they did that, and the periodic table took up the entire wall because they slapped all those guys in the middle and everything was spread out. But they should go there. We don't really deal too much with these guys in this particular class. There are a lot of radioactive elements, sort of man-made elements as well, which are radioactive, you know, things like uranium and things like that. So we don't really deal too much with those guys who are on the bottom. But they are also what are sometimes referred to as inner transition metals. And that is because transition metals are actually the area between group 2 and group 3 on the periodic table. So all these guys, let me just litter it here. All these guys in that area, those guys are all transition metals. Transition metals are obviously metals. One sort of characteristic of transition metals that we will talk about is when we talk about naming, they have the ability typically to form variable types of charges when they do form charges. And that's one of those characteristics. Again, those two on the bottom here are sometimes referred to as inner transition metals, because technically speaking, they should go right about there and in that transition metal. So they're also sometimes referred to as those inner transition metals. Any questions on that there? So obviously you need to know the periodic table, where metals are, where nonmetals are, where metalloids are. You need to know the group numbering, the way periods go, and also the names where the alkali metals are, the alkaline earth metals, halogens, noble gases, where you find the transition metals. Any questions on any of that there? And just a couple other things here. The characteristic shape, obviously, of the periodic table. They did a really good job as they were sort of building it. They left room, and they did put, obviously, people that sort of went together near each other. So elements that typically are in the same group do share similar sort of properties. Also, some in the same period as well. And clearly, as we move kind of left to right on the periodic table, we're going from more metals to nonmetals, which is the upper right part of the periodic table. All right. Any questions on the periodic table? Let's see. As I mentioned, there are some noble gases. There's also some noble metals, and that's gold, silver, and platinum. So that is gold, silver, and platinum, which is like right there. These guys are noble metals. They basically mean the same thing. They will be pretty much unreactive. And obviously they go with very similar sort of properties in a sense of that with our group 8, which is our noble gases. You could put like nitric acid on gold, for example, and nothing will happen to it. Yeah, that's actually how they test sometimes, or used to test. If you're like your gold was really gold, they would put some nitric acid on it. If it still was there, it's good. If it wasn't, then not so good. You know, those are things you can learn when you watch, you know, those pawn shows on TV. All right. So a little bit more about those guys. As I mentioned before, they are monoatomic. For the most part, they're all colorless gases at room temperature, the noble gases. They're very non-reactive. And they're found in nature as a collection of separate atoms that are uncombined. And our noble metals as well are silver, gold, and platinum, all solids at room temperature. And they really are the least reactive of any metals that we have. And then obviously we've touched upon this a number of times up to this point. Again, we have our diatomic molecules, our O2, N2, and our F2, and so forth. And that's what we get when we do a chemical change, for example, with water. If you run an electrical current over it, which we will do in a lab coming up, and you will break water into its elements, which is our oxygen gas and our hydrogen gas, H2O, right? So we got 2 hydrogens over here versus an oxygen. And obviously we could break those guys back into their elements. And as we talked about, you can't go any further than that, obviously. Just some more about that, which we covered, I think. All right, so the structures of non-metallic elements are a little bit different. There are some things that we sometimes will see. We can't have the same element, for example, a non-metal guy, and there are different forms of it, and that is what are referred to as allotropes. So allotropes are really the same element, but they have really sort of a different arrangement of how they are put together. So for example, pretty much if we have diamonds, graphite, and fullerenes, they're sometimes called, they're all really carbon. The difference between pretty much all these guys are basically the way the carbons are sort of laid out together. Diamonds have a specific pattern how those carbons go. graphite are like layers of carbon basically together. And fullerenes basically look like giant soccer balls, like kind of 60 carbons together and almost like a soccer ball sort of arrangement. You obviously get different responses, I suppose, depending on what you give somebody, right? You know, you could go, here's a pencil, it's carbon, it's just as good as diamonds. So I suppose you get the same response maybe. But here you can see they're all carbons, but here's more sheets of carbons, layers of carbons versus this arrangement. And obviously it gives it different properties. There's obviously different properties of between a diamond and graphite. So allotropes are nonmetals, basically the same element, but sort of different ways they're put together, giving them different properties. To finish up on, we also talked a little about ions earlier, but just to make sure we sort of understand it, an atom is neutral, which as we talked about means that it does have the same number of protons and electrons. It is when we change the number of electrons that we do create ions, and we do create two types. One is a cation, and as we talked about earlier, that is a result of losing electrons. And we can represent that sort of in a chemical equation. And that's what this is down here, except it's missing, and here over as well. So if we look at sodium, which again has 11 protons, and a neutral sodium would have 11 electrons, it will lose electrons. It will actually lose one electron and become sodium with a positive charge and an electron. This is a way, sort of an equation form, that we could represent the formation of a cation for sodium. The way we know that this is going to be a cation is on the product side, which is on the right-hand side of the arrow. We see the electron like it's being given off or is being lost. And that is, showing the formation of that cation. Same thing here. If we look at magnesium, magnesium will typically lose 2 electrons. So if we start with magnesium that has no charge, it again should have 12 protons and 12 electrons. Magnesium actually will give away 2 electrons. And when it does, we will result with a magnesium with a +2 charge, and we will have 2 electrons that are given off. So again, this is sort of equation way of showing the formation of a cation. Whenever you're forming anything that's positive, the electron should end up on the right-hand side of the arrow or the product side of the arrow, again, to indicate that is being given off. Any questions on that there? Anions would be a little bit different. We would have sort of that's obviously aluminum. We'll talk about that in just a second. But anions are negatively charged. And again, as we talked about, that is a result of them gaining electrons. And when they do gain electrons, obviously, as we talked about a little bit earlier, they have basically more negatively charged electrons than positively charged protons, hence the extra negative charge. Something like chlorine will actually gain an electron. So we could represent that by putting the electron on the left-hand side of the arrow, like it's being added to the chlorine. And as a result of that, we will end up with a chlorine with a negative charge. Again, chlorine going from 17 electrons to 18 electrons in that particular case. You could do the same thing for fluorine as well. Fluorine will also gain 1 electron and become fluorine with a negative charge. You could also have oxygen that will gain 2 electrons, and it will end up with an oxygen with a -2 charge. Again, the key here, when you write the equations, we see the electrons on the left-hand side of the arrow or the reactant side of the arrow, which indicates that they are being accepted by the element and forming a negative charge. Ions, obviously, as we talked about, are never formed as a result of changing protons, because as we talked about last time, if we change the protons, what happens to the element? It also changes as well, right? So we cannot change the protons, just the electrons. Now, how do we go about naming these? As I sort of skipped over that, there's a couple of ways that we name ions in general. If it is a positive ion, any guy that is positive, we simply would just use the whole name of the element. So Na is sodium, this would be known as the sodium ion. You know, if I had Mg2 plus, Mg is magnesium, it would just be called the magnesium ion. Now, when we have negative ions, they're actually named a little bit different. As you can see there in sort of the center, we actually drop the last part of the name. And if it is negatively charged, we add IDE to the end of it. So chlorine becomes chloride ion, fluorine becomes the fluoride ion, and obviously oxygen becomes the oxide ion, IDE. So guys that have negative charge, sort of the way we name them, drop the last part of the name, IDE at the end of it. If you're naming a positively charged ion, you simply just use basically the whole name of it. Any questions on that there? We're obviously going to get more into naming. There's a little bit more rules than that, but that's generally how you name ions that are by themselves. Either a positive guy or a negative guy that's by itself. When we look at the periodic table, there are certain elements that always will form sort of fixed charges. So pretty much everybody in group 1 will form a +1 charge since they are metals. Everybody in group 2 will form a +2 charge. Skipping over, although they have a few more listed here, it's really aluminum here. That's the one you usually will see is +3. Then this is sort of where the staircase comes down. We skip group 4 and we group 5. Group 5 actually will have a -3 charge, everybody in there. Group 6 will be -2, and group 7 will be -1. So it's kind of +1, +2, +3, skip and go backwards, -3, -2, -1. The reason for that is, typically speaking, as we will talk about, it is the metals that will lose electrons. And so that's why they all sort of become positively charged. And it is the nonmetals, as we'll talk about, that basically will accept electrons or gain electrons. And those guys will result in negative charges, as we see here above the staircase. Now, there are a few more sort of guys that have fixed charges. If you look on the periodic table, right around here is zinc and cadmium, and then hang a left and you got silver. Zinc and cadmium will always form a +2 charge. Again, just those two guys. And silver, no matter what the situation, will always be +1. So those guys have fixed charges. As we will talk about it here, as it says here as well, the transition metals do have variable type of charges. So for example, something like copper in that general area could be +1 or +2, depending on the situation. So most transition metals have variable charges, and the only three that really don't is sort of this backwards L here. These guys are fixed charges within that transition metal region. Now, you also should remember there really is no good pattern here for 4, because up on top is nonmetals, we got some metalloids, and then we have metals that are underneath there. So below the staircase, they are metals, which would be positively charged. So even these guys in group 3, which are negative, or group 5, which are -3, if you go below the staircase, you're back into metals like lead and bismuth and all those guys, which are positively charged. Any questions on that there? Now, compounds that contain electricity, ions, are really good conductors of electricities. So when we dissolve anything that has ions into a solution, it's able to really conduct electricity really well. And those are what electrolytes are known as. So electrolytes are things that when you dissolve it into solution will create ions. It is those ions that help kind of complete the circuit, if you will, and allow it to conduct electricity. So for example, if you took something like sodium chloride in water, when it goes into water, it's going to 100% break apart into sodium ions and chloride ions. So in water, we would have sodium ions and chloride ions 100%, which means it will be able to conduct electricity really, really well because there's a lot of ions that are basically floating around in there. If you kind of use a light bulb as an example, and you did that, a light bulb that was hooked up to some electrodes, and you put it into a sodium chloride solution, the light bulb would go off very, very brightly. So it will be very, very bright. There are also some that are weak electrolytes. And weak electrolytes mainly stay together, but break apart a little. So if we look at something, for example, like hydrofluoric acid, it is actually a weak electrolyte. When it breaks apart, it will break apart into H+ hydrogen ions and fluoride ions. And it will mainly stay together as this whole thing. But we do get a little bit of these ions that are formed. And because it's still able to put a little bit of ions floating around in solution, if we go back to the light bulb example, you kind of put it in with the electrodes, the light bulb would turn on, but it'd be very, very dim. So not a lot of electricity going through there. It won't be able to conduct electricity anywhere near like a strong electrolyte, but it will still be able to do that. There's also non-electrolytes. Non-electrolytes pretty much do not produce ions, which means that they can dissolve. So an example of that would be something like sugar. If we take some sugar and we put it in water, it dissolves. Sugar is really a molecular compound, which means it stays together. It doesn't make ions, nothing with charges. So because it doesn't create anything that has charges, it will not conduct electricity, which means, again, if you kind of put the light bulb example in there, the light bulb will pretty much stay off. It will not come on. It will not conduct electricity. Is pure water a good or bad conductor of electricity? It's actually a bad conductor of electricity, pure water, because water is a covalent compound, which means it never breaks apart. It stays together, all the parts of it. So it's actually a really bad conductor of electricity. And with that being said, clearly the water that comes out of your faucets is not pure water. Yes, they actually put ions in it to help clean it. And that means there's a lot of ions in there, which means you will electrocute yourself if you do something with water, obviously, and listen to the radio or something like that, or blow dry your hair in there, you will definitely get electrocuted. But if you have pure water, because it's technically covalent, listen to radio while you're blow drying your hair in the shower, not a good idea, just so we're clear. So we're clear on that recording there. Do not do that. That's not a good idea. But if you have just pure water, just H2O, and obviously, because there's really no ions present, it's actually a pretty bad conductor of electricity. Again, please don't play with electricity and water. All right. Here's that sort of example. So, if we hooked up something like this, like pure water here, again, it really has no ions. So we can see the light bulb obviously does not go off. If we put some salt, which is really just sodium chloride, this guy has a lot of sodium ions and chloride ions floating around in there. A lot of those ions, again, going to help complete it. You can see light bulb goes off. And like I said before, if you did something that's sort of a weak electrolyte, like hydrofluoric acid, and by the way you can recognize a lot of times weak electrolytes is if you look at the equation, you will actually see two arrows, and you'll see arrows heading in both directions. And that means that this reaction is what is referred to as being reversible. There's a forward direction where everybody is going in this way, where reactants go to products. But in these type of reactions, at some point, the products will decide we want to come back the other way, which is sometimes referred to as the reverse direction. And at some point, it will reach what is referred to as equilibrium. It will go one way just as quick as it comes back the other way, and you'll kind of balance. You won't really get the same amount on both sides, but everybody will lock into place as the rate is the same as it's going forward and reverse. So that's a really key sort of thing. If you see those reversible arrows, that's definitely a weak electrolyte, which means you pretty much have whatever's on the left-hand side of the arrow is mainly what's there, but you still get a little bit of ions that do form on the right-hand side. And again, if you did that, we'd have more of a dim looking light bulb there that would go off. Any questions on that there? So whenever a compound forms between a metal and a nonmetal, it is expected to contain ions. These substances are ionic compounds. This is basically how something like sodium chloride in the solid form is. We have these sodium ions and the chloride ions. Why are the chloride ions larger than the sodium ions? Any ideas? Well, it has to do with the idea that in order for that guy to become negatively charged, it had to gain electrons, right? Which means this electron cloud gets larger. In order for the sodium guy to become positive, it had to lose electrons, which means its electron cloud got smaller. So when we look at the size of a cation, the positive guy versus this neutral guy, it will always become smaller because it's losing those electrons. So overall, the whole thing kind of shrinks, as opposed to negatively charged ions. And compared to the neutral, they typically get larger because they are increasing electrons in their electron cloud, and they become larger as you do that. By the way, this is what happens when water comes in. Water is actually what is referred to as a polar molecule, which basically means that there is a positive side of the water, which is the hydrogens, and a negative side, which is the oxygens. And basically, water comes in and plucks each of these guys off. And for example, the chloride then gets surrounded by the hydrogen part of water all the way around, a ton of waters, which again makes it appear to us that the sodium chloride has disappeared. Same thing happens with the sodium ion. It gets surrounded by water as well, but it actually gets surrounded by the oxygen side of water. And that's really how, when we take something like sodium chloride and put it into water, like I said, it kind of looks like it just goes away. It's gone. It's really because lots and lots and lots of water surround each of the ions that are in solution, and it sort of visually disappears to us. As we know, it is still there as we evaporate off the water, right, in some experiments, and the salt came back. But that's why it sort of disappears. That's why it also keeps the two ions from coming back together. When those waters get out of the way, like when we evaporate off the water, there's nothing between the positive guy and negative guy, and that is a super strong attraction, and they pop back together. And that's when we do see the solid return, when we sort of evaporate off the water, and we do that. When we usually have something that's solid, we also do what? Usually we mix it, right? So that supplies a lot more water over a greater surface area of the solid, also supplies energy, allows the dissolving process to occur a lot quicker, right, than just you drop the solid in there and hope for the best that it dissolves. Any questions on that there? Yeah. Yeah. It is still a physical change because, again, the water part of it is still water, right? And the chloride part, which started with the sodium ions, are still there in their original form. It's just that they have sort of changed states, if you will. They went from solid to being aqueous, which is a state where they're surrounded by water, basically. And we know it is a physical change because, again, when we evaporate off all these waters, we could collect it, right? But it comes off as steam, which is still water. And by getting rid of those waters from those ions, these two guys would come back together, back to the solid sodium chloride like it started with, which again is his original form and would be a physical change that occurs now. Yeah, so the dissolving of, like, really even like something like hydrofluoric acid in water, it's still really, just a physical change. It's just hydrochloric acid or hydrofluoric acid, either one. That's basically that's basically what it is. So I'll put it this way. So it really is a physical change. In order to have something, let's say like hydrochloric acid, you basically have to have the H plus and Cl minus in there. Although we represent that in a sort of equation form like this, this is really just the process of it dissolving in water. And we can use equations to represent physical changes that occur. Like if we had water in the solid state to water in the liquid state, right? We could write an equation for that. And that's a physical change that occurs. So this is really a physical change. In order to, hydrochloric acid has to be in water for it to be an acid. Otherwise, it would be a gas. It would be hydrogen chloride gas is really what happens before you get the hydrochloric acid. You take the gas, you bubble it in water, you get the ions that get formed, and now it becomes hydrochloric acid in water. But it's really more of a physical change. All that is only going to be a chemical change in an equation if you see really on the reactant side of the arrow multiple things kind of together, like this plus this reacting. That's really going to be more of a chemical reaction, chemical change. Sometimes we do use sort of equations to show physical sort of changes that are occurring. Other questions? Now, also when we talk about ions, it's really important that whenever we put together a positive ion and a negative ion, the overall charge is actually going to be 0. So you want it to be a neutral compound. And we'll take a look at each of these in just a second here. So overall, we want the overall charge to really be 0. And we want to put together the positive ion and the negative ion in the simplest way that you could achieve 0. So for example, sodium, which we know when it does form a charge is +1. Chloride is -1, which means if we simply put these guys together, +1 and -1 balance out to 0. And we do get the formula, which is sodium chloride. And again, the chemical formula for an ionic compound, which is this, should never have a charge. So the NaCl should not have a charge. But it is actually made up of two things that do have charges. So it's actually made up of two things with charges. If we look at calcium and chloride, if we were to just throw these guys together as is, would we end up with an overall charge? If we take +2 and -1, we're left with +1, right? Which is an overall charge. So to balance this out, we need not one chloride, but we actually need 2 of them to balance it out. -1 and -1 gives us a -2 on the right to balance out the +2 on the left. And that gives us the proper formula for this, which is obviously 1 calcium and 2 chlorides in this particular case. Same thing here. If we look at barium with a +2 and oxygen or oxide with a -2, +2 and -2, when we put it together will equal 0. So we just need 1 of each. If we look at aluminum, which is +3, and we look at sulfide, which is -2, again, if we just put them together like that, we would end up with an overall charge, which is not what we need. We could look at both of those, and the common number between 3 and 2 is 6. In order to get aluminum to 6, we need not 1, but we need 2 of them, right? +3 + 3 is +6. To get sulfide to 6, we need 3 of them. -2 -2 -2 is -6. That gives us the proper formula of 2 aluminums and 3 sulfides in that case. And that gives us our formula that we look at that does not have a charge when we put them together. Any questions on that there? Lastly here, potassium and phosphorus. Again, potassium being +1, phosphide actually being -3. In this case, we actually need 3 of the potassiums, +1, +2, +3, to balance out the phosphide. And that gives us K3P as our proper formula here. Again, overall no charge. Any questions on that? So whenever you write a formula for an ionic compound, always want to make sure the overall charge is 0. Now, sometimes people learn to do it this way. I'll just do this. like I'm going to move the charge down or move the charge up. And that works, about 95%, 93% of the time. Doesn't work 100% of the time. So I would not blindly just switch sort of the charges. Again, it works most of the time, but there are a lot of exceptions to where it will not work. So the best way to think about it is just to make sure you are balanced it out to 0 in terms of the charge. Any questions on that there? By the way, if we put together the name, as we'll talk about in a later chapter, aluminum, we would use the whole name, and sulfur becomes sulfide. That would be aluminum sulfide would be the name of that guy. Obviously here, sodium, the whole name. IDE for the chlorine becomes sodium chloride. Again, that's sort of how we get some of the names. There are more rules, which we'll talk about in that proper chapter there. Okay, so we're going to go to chapter 11 here. We're going to talk about a little bit about modern atomic theory. We're going to talk a little bit about sort of waves, but mainly in this chapter, we're going to really focus in on electrons. We're going to talk about electron configuration. We're going to talk a little bit about sort of the energy involved with electrons. So as we talked about with Rutherford, the basic idea was described as really the atom having a positive core, and we have these negatively charged electrons, as we talked about, really flying around the nucleus at some distance, as we'll talk about, as we'll see sort of in this chapter as well. Again, those electrons are traveling in a pretty random pattern around the nucleus. We also talked about the idea that obviously there is some attraction between those electrons, which are flying around in that empty space or that electron cloud, and the nucleus, as the nucleus is positively charged and the electrons are negatively charged. The nucleus, as we know, is very small compared to the size of the atom. So the electrons really do make up a vast majority of the volume as they're flying around in that empty space. But remember that most of the mass of the atom is made up of the nucleus, which has those protons and neutrons that are more massive than those electrons. So a lot of work was done early on with waves and electrons by a guy named Planck. And he did a lot of work sort of heating various sort of metals and solids to different temperature. And one really idea that comes out a lot when we talk about sort of electrons, and really in sort of our application, is the idea of how electrons, for example, go from one energy level to the next and kind of travel from different energy levels within the atom, is this idea of a quanta or quantum of energy is released. And when we talk about sort of a quanta of energy, we'll see some other sort of demonstrations of this a little later on. But the idea here is that energy is either gained or released in certain quantities that allows things like electrons, for example, to go from one energy level to the next. So the idea of a quanta of energy is the idea that if we had an electron on, say, this energy level on the bottom, it would gain enough energy to kind of completely get itself up to the next energy level, or whatever energy level it's going to, and it won't stop in between. So the very common example, I think we'll see a picture later, is like the idea of like stairs, right? When you walk stairs, you typically have enough energy to get to this step, the next step, the next step. You don't usually find yourself halfway between a step and go, I'm a little tired, I'm going to lay it up right there. Maybe you do, but you don't stop there usually between the two steps. Otherwise you would fall. And that's sort of the idea that sort of came out of this, is as electrons sort of transition from different energy levels, they either gain enough energy to go to a specific energy level, or they could even go from a higher energy level back down to a lower energy level, which would require them basically to lose energy to do that. And they would lose enough energy to make that transition sort of completely from one energy level to another. And as these things like electrons are sort of transitioning from one energy level to the next, they are sort of giving off this energy really in the form of a wave. And a wave is sort of the emission of energy through space. And a wave, could be radioactive or radiation, but a wave is something that looks like that. And it obviously carries a certain amount of energy either into the atom or away from the atom as these guys are transitioning from one energy level to the next. So let's talk a little bit about a wave. The wave can be thought of as this sort of vibrating disturbance, which energy is being transmitted from. The bird here is in the same location, but the wave is passing them by. Seems like a good day. Go to the beach. The speed of the wave does depend on obviously what it's traveling in and the medium at which it is. It can affect obviously the energy of it. So let's talk about some important parts of a wave. The first important part is the wavelength, or lambda is sometimes referred to. And if we look at the wavelength, it is basically the distance between two peaks or a trough on the bottom. It is usually in units of meters, centimeters, or nanometers are very common units that we see for the wavelength. The frequency, or nu, which some people call V, it's really not a V, but it's nu, is really the number of waves that pass through a particular point per second. And it usually has units of reciprocal seconds, or 1 over a second, which is the same thing as a hertz. So a reciprocal second is the same thing as a hertz. It's a 1-to-1 relationship. And that is like your radio, right? When you tune it to 95.5 megahertz, right? That is the frequency in which that radio wave is coming through, just in case you're curious about that. The amplitude of the wave is the vertical midline, kind of from the peak to the trough. And the speed of the wave, which is sometimes abbreviated with sort of a U, is given by the product of basically taking the wavelength times the frequency there. And you take the wavelength times the frequency. Again, wavelength typically in meters, frequency typically in 1 over seconds, which usually when we talk about the speed of a wave gives us units of meters per second. Is a very common sort of units that come out when you calculate the speed of a particular wave. Any questions on that there? And there's all those things we just talked about there. Now, light does behave like electromagnetic radiation, and electromagnetic radiation sometimes have properties that are characteristic of particles and also properties that are characteristic of waves. So a lot of times when this sort of stuff, and we're not going to go into super deep detail on all this stuff, but you sometimes hear a lot about the dual nature of light. And that basically is some ideas that came about in these sort of experiments during this time, that, waves can have functions or characteristics that are very similar to what we see with particles, and particles themselves, like an electron, can have characteristics that are very similar to waves. So they kind of have that dual nature. Things have both some wave-like functions and also particle-like functions as well. And they're specifically related to electrons, can have both of those sort of characteristics. One can think of a beam of light traveling through space as these tiny packets, which are known as photons of energy. So again, sort of relating this to really the application here, what we're talking about, as we talked about an electron sort of transitioning to a higher energy level, eventually what's going to happen is, in most things in chemistry, things like to be in a lower state of energy. So eventually that electron that sort of gets excited and kind of goes to a higher energy level, it eventually is going to want to work its way sort of back down to a lower state of energy. In order to do that, would the sort of atom need to gain more energy or lose energy in the case of this? It would have to lose energy, right? So as that electron is transitioning down, it's got to lose energy to go from a higher state of energy to a lower state of energy. The result of that is the atom will typically give off energy in the form of a wave. And that is what is sometimes referred to as photons that are given off. Now, if this wave that's coming off has a specific wavelength in the visible part of the spectrum, the visible part of the electromagnetic spectrum, as we will see in a later slide, is the part where we see colors, like Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. If it happened to come off in that wavelength, we would see a color light. Hence, when we see fireworks, right, we see colors. What happens is they explode the fireworks, gains a lot of energy. Electrons and the elements jump up to higher energy levels. They decide all to come back down to lower energy levels. When they do so, it gives off energy in the form of visible light, where we go, oh, it looks pretty, it's blue, it's red, it's green, and all those type of things. And those are because of those electrons have been excited and they coming back down as a result of those fireworks basically exploding and gaining all that energy and then relaxing back down. And we see it obviously as color. Sometimes it may not come off in the visible part of the spectrum. It may come off in something like the infrared part of the spectrum, where we feel heat, we feel like warmth and stuff like that coming off as a result of these electrons transitioning. So there is a relationship between the wavelength and the energy that's associated with it. If we have a long wavelength like this, we typically have a long wavelength, which means we have a shorter frequency, or longer frequency, I guess would be a better way around that if I can do that. Longer frequency. And that's usually lower in energy. So when we see a wave that has a really long wavelength, it takes a long time for it to sort of occur. It's associated with a much lower energy, as opposed to a wave that has a much shorter wavelength, a higher frequency. It occurs a lot more often, and that's usually associated with higher energy. Even things like colors have differences in energy. Red is actually a lot less energetic than actually violet. So purple is a lot shorter wavelength, higher energy associated with that color, as opposed to something that is sort of red in color. Any questions on that there? So here is a light as a wave, again, having wave-like functions, but also have these particle-like functions where they have that dual nature that can travel like particles, and they also can travel and have wave functions. And here's, as I mentioned before, red versus blue. Red would be a lot less energy than the blue light. Again, the blue has a lot more energy, shorter wavelength versus our longer wavelength there in red. Now, there are some characteristics with electromagnetic radiation or waves, and that is the speed of light. And the speed of light is abbreviated with a c, and the c is 3 times 10 to the 8 meters per second. And we could actually use this equation here to calculate things like wavelengths of waves, frequency, or the speed of it. And that is the speed of light, which is that 3.0 times 10 to the 8 meters per second. Obviously, again, that is our wavelength. That needs to be in meters, and that is our frequency. That is in reciprocal seconds. So if you wanted to know the wavelength and you know the frequency, it would be the speed of light divided by the frequency. And if you want to know the frequency for a particular wave, and you know the wavelength, it is c divided by the wavelength. So that's a formula that we don't use too much in this class, but you will use in what do they call it here, 1A, I think. Yeah, so 1A, you'll use that a lot, but that's a way you could calculate the wavelength or the frequency if you know either the wavelength or the frequency. C is a constant, and you always have sort of that number available to you. As I was talking about before, this is what was referred to as the electromagnetic spectrum. And there are different parts to it. For example, if we look on this side of the spectrum, this is a much longer wavelength. And on this side to the -12 is a much shorter wavelength. That means to the left there is higher energy, and to the right is lower energy. So lower energy on this side, higher energy as you go this way. So if we look sort of on the right-hand side, we have, radio waves. So as we were talking about earlier, listening to the radio, the TV, not too bad for you in terms of energy. As we proceed to the left, we have microwaves. Microwaves have a little bit more energy, enough energy to spin the water molecules in your food really fast. And you get a pizza in like 3 minutes, not too bad. Continuing down this way, we get infrared. That's typically where we see heat and stuff like that. Next is the visible part of the spectrum, and that is where we see our colors. So again, our Roy G Biv coming this way here. And that is red, and that is supposed to be purple there at the end, or violet. And these guys are typically given in nanometers. So when we sort of quote the wavelength for sort of the visible part of the spectrum, it's typically given in nanometers, 500 nanometers, 700 nanometers, something like that. But we do see, again, as I mentioned, red is lower in energy versus violet, which has a smaller wavelength. And again, next is ultraviolet, which has a little bit more energy. It's also why we put sunblock on right when we go outside, so we don't get too burnt or anything like that. X-rays has a little bit more energy, obviously. That is why they put a lead vest on you to step out of the room usually when they take the X-ray. And over here is gamma rays. Gamma rays is basically just pure energy. It's a radioactive sort of ray, and it's basically very, very high in energy. So depending on sort of the application, what we're talking about here, again, those electrons transitioning up or down, and that wave of energy that comes off, it may fall somewhere along the spectrum. Again, if it falls somewhere in this visible part of the spectrum, you will see color depending on which the wavelength is. Again, if it falls outside of that, like over here in the infrared, again, you may feel heat or something like that. So it won't always produce a color depending on the transition. But a lot of times we do see sort of colors. Flame test, which I think we're going to do next week, or maybe if you've done a flame test, it's the same idea. You take some elements, you put it into a fire, the fire heats everybody up, electrons get excited, they come back down, you see a color. You maybe have done a flame test at your house without realizing it. Maybe you boiled water on your cooktop and the water over boils, and if you have a flame underneath it, flame changes color as the water hits it, and that's a lot of times the sodium that's in there, and it'll change to like an orangey color really quick as the sodium sort of burns and stuff like that off of it. You do need to know the electromagnetic spectrum here in terms of the order. You won't be asked specific wavelengths or anything like that, but you need to know kind of radio waves is longer wavelengths, shorter, lower energy than microwaves, and so forth. So you may be asked a question to put these guys in order based on energy, highest to lowest, or wavelength, longest to shortest. That's sort of what you need to know, not exact numbers. That also includes the colors, being able to put the colors in order from longest to shortest wavelength, highest to lowest energy. Any questions on that there? All right, we will lay it up